Good day, class. Welcome to our 11th lesson in organic chemistry. In our previous lesson, we started looking at the carbonyl compounds, where we said the carbonyl compounds are made up of aldehydes and ketones. And we also looked at the carbonyl group being highly polar. As such, dipole-dipole forces between the molecules are quite significant. And these dipole-dipole forces between the molecules leads to high melting and boiling points of the carbonyl compounds than the alkanes of comparable relative molecular mass, but lower melting and boiling points compared to alcohols of comparable relative molecular mass. We also looked at the physical properties, where we saw that, with an exception of methanol, all simple carbonyl compounds are liquid at room temperature, and the earlier members of both series are considerably less volatile than the alkanes of corresponding relative molecular mass. We started looking at the reactions of carbonyl compounds, where we said they burn in excess air or oxygen to yield carbon dioxide gas and water. They undergo oxidation reaction in the presence of orange solution of dichromate to yield a green solution of chromium 3 ion, and carboxylic acid is being produced. But ketones are not readily oxidized to carboxylic acids with same number of carbon atoms. We also looked at their reduction reactions, and we said the carbonyl compounds, that is aldehydes and ketones, can be reduced using hydrogen with a catalyst of nickel or platinum. And we also concluded that the aldehydes are going to yield primary alcohols, while the ketones will yield secondary alcohols. They also can be reduced using lithium aluminum tetrahydride in dry ether solution, followed by the addition of water. And also, they are reduced using Clemens's reagent, whereby they are reduced to the corresponding alkanes. We said the addition reactions are being influenced by two factors, that is positive inductive effect and steric hindrance. Today, we are going to continue with the addition reactions. Whereby we looked at that they react with hydrogen cyanide to yield hydroxyl propanoyl compounds. Today, we are going to be looking at their condensation reactions, that is, addition-elimination reactions, whereby an atom or group of atoms is being added and another atom or group of atoms is being eliminated from the carbonyl compound. This elimination and addition reactions, that is called condensation reactions, are addition reactions which are followed by the elimination of water. Two molecules combine with the elimination of a water molecule. This involves derivatives of ammonia, and they are of general form H2N X. These derivatives of ammonia include hydroxylamine, hydrazine, phenylhydrazine, and 2,4-dinitrophenylhydrazine. Looking at a general reaction of the condensation reactions. We're going to see that. You can look on your screen, you see the mechanism. And we said the carbonyl group is highly polar, and the carbon atom of the carbonyl group is a carbonium ion, that's a positive charge, and the oxygen is negative charge. If you look at the ammonia derivatives, and you see that they are also polar, whereby hydrogen ion, which is a positive ion, is going to have an arrow coming from the negative ion of the carbonyl group. And you see that at the end of the reaction, water is being eliminated. The first condensation reaction we'll be looking at is the reaction with hydroxylamine. They react with hydroxylamine to form an oxime. For example, ethanol oxime and propanol oxime. The second reaction is the reaction with hydrazine. They react with hydrazine to form hydrazone, such as ethanol hydrazone, propanol hydrazone. And note that all of these reactions follow same reaction mechanism. The third reaction type we'll be looking at is their reaction with phenylhydrazine to yield phenylhydrazone. You can see the structure of phenylhydrazine there. An example we have there is ethanol phenylhydrazone. We're going to look at the fourth reaction type there is their reaction with 2,4-dinitrophenylhydrazine. They react to form 2,4-dinitrophenylhydrazone, such as the 2,4-dinitrophenylhydrazone obtained from ethanol, that is ethanol 2,4-dinitrophenylhydrazone. This is a general test, that is the reaction with 2,4-dinitrophenylhydrazine. It's a general test used to identify the carbonyl group in aldehydes and ketones. A yellow precipitate is normally formed by both aldehydes and ketones when reacted with 2,4-dinitrophenylhydrazine, which means that the color of 2,4-dinitrophenylhydrazone is yellow. As such, 2,4-dinitrophenylhydrazone is a yellow precipitate. The fifth reaction is the reaction with a semi-carboxyl. Now, we are going to be looking at distinguishing between aldehydes and ketones. We know generally that aldehydes are more reactive than ketones due to the steric hindrance of the arrow groups, whereby the aldehydes have just one arrow group attached to the carbonyl group, and the ketones have two arrow groups attached to the carbonyl group. The first test we'll be looking at is the iodoform or chloroform test, and this is a test for carbonyl compounds. This test confirms the presence of aldehydes and ketones in a compound. They react with both chlorine or iodine. If iodine or chlorine and ethanol, for example, or propan-2-on are warmed in the presence of a base, the trichloro or triiodoethanal or propantuone is formed. This triiodo or trichloroethanal or propantuone reacts with a base to form trichloromethane, that's chloroform, or triiodomethane, that's the iodoform test. As you can see from the reaction there, we have ethanal reacting with 3 molecules of chlorine in the presence of heat or warmth to yield trichloroethanal and hydrochloric acid. We have trichloroethanal in the presence of a base, warm, is going to give us a trichloromethane and carboxylic acid. Then further, we also see that ethanal also reacting with 3 molecules of iodine being warmed is going to form triiodoethanal. This triiodoethanal, like we earlier said, when it reacts with a base, it forms triiodomethane. And this triiodomethane reacts with a base is going to yield a yellow solid, which is the test for the presence of carbonyl compounds. This yellow solid is triiodomethane. Iodoform is a yellow solid with a characteristic smell. It is insoluble and appears as a yellow crystalline precipitate at the bottom of the container, that's at the bottom of the test tube. Tournaise reagent, or the silver mirror test, is another test used to identify carbonyl compounds. The Tournaise reagent is a solution of 6.6 ammonium and nitric acid with a trace of silver oxide. The essential ions in Tournaise reagent are silver ammonium ions, that's diamine silver 1 ions. Tournaise reagent is colorless. On adding aldehydes, the silver complex, which is colorless, is reduced to a gray precipitate of metallic silver. In a thoroughly clean test tube, the silver mirror will be formed on the inside, that is, on the wall of the test tube. You can see the gray precipitate of silver solid being deposited on the reaction there. We have methanal in the presence of diamine silver 1 ions and water being warmed. It's going to form gray precipitate of silver solid and ethanoic acid and ammonium ion. Ketones give no reaction with the Tournaise reagent. The next we're going to be looking at is Fehling solution. Fehling solution is an alkaline solution of copper 2 ions complex. This copper 2 ion is complex with 2,3-dihydroxybutene diurate ions. The essential ions in Fehling solution are copper 2 ions. When the solution, that is the Fehling solution, is boiled with an aliphatic aldehyde, it reduces the blue solution to a red precipitate of copper 1 oxide. Note that since the Fehling solution has the main or the essential ion as copper 2 ions, the color of copper 2 ion is blue. Thus, the color of the Fehling solution is often blue. And in the Fehling solution test, we see that this copper 2 ions, which is a blue solution, is being reduced to copper 1 oxide, which is a red solution. As such, the copper 1 oxide forms a red precipitate. Aromatic aldehydes, for example, the benzaldehyde and ketones, give no reaction with the Fehling solution. The next test is the aldol condensation. Aldehydes with alkyl hydrogen next to the carbonyl group undergo this reaction to produce an aldol. An aldol is made up of an aldehyde and an alcohol. Only aldehydes with alkyl hydrogen atoms such as ethanol, propanol undergo this reaction, while aldehydes without alkyl hydrogen atoms such as methanol and benzaldehyde do not undergo this reaction. When an alkyl aldehyde with alkyl hydrogen atoms is reacted with cold dilute alkali, it diminishes to form an aldol, such as the 2-hydroxybutanol on your screen there. Another test is a deproportionation reaction. This deproportionation reaction takes place in aldehydes without alkyl hydrogen atoms. That is, this deproportionation reaction takes place only in methanol and benzaldehyde. Meanwhile, aldol condensation doesn't take place in methanol and benzaldehyde. Under this disproportionation reaction, we see that when an aldehyde, to be precise, an aldehyde without alkyl hydrogen atoms, is treated with concentrated alkali at room temperature and pressure, it undergoes simultaneous oxidation and reduction to produce an acid and an alcohol. For example, we have methanol in the presence of concentrated hydroxy ion that represents a base or an alkali. It's going to give the oxidation. The product there is going to be methanoic acid, and the reduction product is methanol. Also, in the polymerization reaction, carbonyl compounds can form polymers by addition across the carbonyl group, that is, by addition across the carbon to oxygen double bond. Ketones do not polymerize easily. Aldehydes are readily converted to a variety of addition polymers. Methanol, for example, polymerizes more readily than the other aldehydes. Methanol, when aqueous solution of methanol is evaporated, polymethanol is produced. When polymethanol is heated in an acid medium, it breaks down to form methanol trimer. Now you can see on your screen there we have the polymethanol and methanol trimer. Looking at the polymerization of ethanol, you see that ethanol forms 3 types of polymers. The polymers are different because of 3 different conditions. The first condition is when a few drops of concentrated sulfuric acid is added to ethanol. Ethanol trimer is formed. The reaction is an exothermic reaction, that is, heat is being given out. And the second condition of ethanol forming another type of polymer is when hydrochloric gas is bubbled through ethanol trimmer. Ethanol tetratrimer is formed. Also, when concentrated alkali such as potassium hydroxide or sodium hydroxide is treated with ethanol tetramer, the alkali catalyzes the polymerization of ethanol and polyethanol is formed. Methanol trimmer, ethanol trimmer, and ethanol tetramer have cyclic structures. These cyclic structures are obtained when the respective monomers are linked together through oxygen atoms. For example, we have the structure there of ethanol trimmer. You see the cyclic structure whereby each carbon atom in the cycle is being bonded to an oxygen atom. And the same cyclic structure with ethanol tetramer. Comparison of reactivity of aldehydes and ketones with nucleophiles. We realize that both aldehydes and ketones undergo nucleophilic addition reactions and addition-elimination reactions, that is, their condensation reactions. And both nucleophilic addition reactions and addition-elimination reactions involve nucleophilic attack on the carbonyl carbon atom. That is as such. Aldehydes react more readily than ketones for two reasons. The first reason is that in the ketones, the electron releasing, that is the inductive effect of the two alkyl groups, reduces the positive charge on the carbonyl carbon, making it less easily attacked by nucleophiles. That is, like you can see on your screen there, you find that ketones have two arrow groups releasing electrons to the carbon of the carbonyl group, thus making the carbonyl carbon more stable than the carbonyl carbon in aldehydes. The carbonyl carbon in aldehydes is less stable than the carbonyl carbon in ketones because the carbonyl aldehyde has just one arrow group attached to it, which releases electrons to the carbonyl carbon. For this reason, aldehydes are more reactive than ketones. The second reason why aldehydes are more reactive than ketones is that the two alkyl groups of a ketone tend to get in way of attacking nucleophiles. This is sometimes called steric hindrance. Today we've come to the end of our lesson on carbonyl compounds. And in our next lesson, we're going to be looking at halogenoalkanes, which are another class of hydrocarbons, that is, straight chain hydrocarbons containing halogens.